Well, that was 10 minutes, so let's get back into the swing of things. So from this point on, is material that will, or can, and most of it will be covered on the exam. So I will start taking notes now. The best advice I can give to you is go on D2L, download the slides, and either print them out, have them with you, or have them on your tablet or your iPad or whatnot. Excuse me, that way you can have them to follow along with, and that way you don't have to write as many notes. Because if the more you can listen and the less you can write, I think the better you'll do. All right? So, but if you're one of those people that just has to write, feel free. I may jump off of a slide before you get a chance to write everything down. But don't worry, don't freak out. Everything that I have on the screen is on D2L. Everything. Actually, more than I put up on the screen is on D2L. Okay? So if you miss something, you can get it back. It's on Desire to Learn. Okay? All right, Chemistry and Chemicals, Chapter 1. Chemistry, the study and composition, structure, properties of matter. And chemistry happens all around you every day, and it happens inside of you. Sorry, Devin, didn't mean to hit the mic. Everyone say hi to Devin.
Hi, Devin.
Hi, Devin. All right. It happens every day, all around you, and inside of your body. All of your cells are doing chemistry all the time. If they weren't, you couldn't live. You couldn't move. You couldn't walk. You couldn't see. Chemistry is happening all the time. Now, we have a glass of water, and we're putting in 2 tablets of stuff, and we're getting some fizzy action going on. Effervescence is the fancy word for it. Plop, plop, fizz, fizz. We all know what that is, right? You're all too young. It's Alka-Seltzer. Alka-Seltzer's big tagline was plop, plop, fizz, fizz, and it gave you that nice effervescence, so you always felt like something good was happening in the glass, and when you chug-a-lug it down, you felt like something good inside your body. Matter. The word matter, M-A-T-T-E-R, is a fancy word for saying everything. Matter is a catch-all word that encompasses everything on the earth. I am made of matter. You are made of matter. The floor is made of matter. This table is matter. Everything is matter. The paint on the wall, the air in the room is matter. Glass, air, everything. It's a catch-all word for everything. All substance is made of matter. Your cat, your dog, the plants in your windowsill, they're all made of matter. Chemicals. Chemicals. Substances that have the same composition and properties wherever you find them. So that's interesting. That's an interesting phrase. A chemical is a thing or substance, matter, that has the same composition and property wherever you find it. Interesting. Let's think about a chemical that we can find all over the place. How about water? Is the water in South Florida different from the water in northern Canada?
Yes.
How is it different?
Well, I believe the water, from what I hear, the water in New York, because they filter the water.
Aha! Good point. See, now we're talking about something different. We're talking about mixtures. I'm saying the water itself, just the water, that the rain that falls in New York, the water that's in the rain, not the other things that might be dissolved in the water, but the water itself. Is it the same in New York as it is in Florida, as it is in Canada? It has to be, right? Water is water is water. If you brought ice from northern Canada, brought it to Florida, thawed it out, purified it so there's no bacteria in it, and drank it, it would be the same as the water here, wouldn't it? It would hydrate you. It would make you stay alive. It's the same. Sugar. The sugar that you put in candy in Florida is the same as the sugar that's in the candy in Canada or in Europe. Sugar is sugar is sugar. It's all the same. Has the same properties no matter where you find it. Oxygen. The oxygen in the air is the same as the oxygen that's in Europe, that's in China, that's in South America. It's the same oxygen. It's the same properties, has the same material no matter where you find it. Those are chemicals. And the book likes to talk about toothpaste because pretty much everyone uses it for the most part. Everywhere you look, you'll find a whole list of chemicals. Don't write these down. Just look at the list. This is in your book if you want to see it. If you look at the tube of toothpaste, you will see a tremendous amount of chemicals in there. First one on the list, calcium carbonate. Calcium carbonate is found in a lot of things, not just toothpaste, but it's also found in toothpaste. And what does it do? It's an abrasive. It just kind of chews off the plaque. No big deal. Sorbitol it prevents the water from getting hard. The sorbitol in the toothpaste in Florida is the same as the sorbitol in the toothpaste in Europe. It's the same. Glycerin, that's kind of boring. Sodium lauryl sulfate. Wow. Sodium lauryl sulfate? What's that? That's a detergent. What? Putting soap in your mouth? Yep, you're putting soap in your mouth. Isn't that cool? Titanium dioxide. Titanium dioxide is a very fancy chemical. It's brilliant white. The same titanium dioxide they put in toothpaste to make it look bright white is the same titanium dioxide that some paints have to make them bright white. Titanium dioxide, no matter where you find it, it's the same thing. It's at different uses. Let's go all the way to the bottom. Methyl salicylate. Now that sounds like a chemical, doesn't it? Methyl salicylate. Let's imagine you had your newborn baby. Or your children, not newborns, let's say they're like toddlers. Would you give them methyl salicylate? Would you just say, here, have a spoonful? No, because it sounds gross, right? Ew, methyl salicylate. It sounds all chemical and stuff, not natural. Methyl salicylate is wintergreen. Would you give your child wintergreen? You would, right? Because it sounds natural and awesome. Methyl salicylate sounds like a chemical. Wintergreen, methyl salicylate are really the same thing. They both smell good. They both taste the same. They are really the same thing. They just have a different name. Wintergreen, methyl salicylate. Kind of fun, right? All right. Which of the following contains a chemical? So of those three things on that list, which of them would contain chemicals? Milk. Milk definitely has chemicals in it, right? Milk has, first of all, has water. So that's a chemical. It has fat. That's a chemical. What else? Sugar. Lactose, right? Vitamin D. Those are all chemicals, right? What about fruit?
Yeah.
Oh, for sure, right?
That's how you make alcohol, right?
I like how you think. Yeah, that's one way to make alcohol. You can ferment fruit. Fruit has sugar. It has color. It has some kind of nice smell. Remember, you could, like a peach, you can smell peach, right? It has a nice odor to it. Those are all chemicals that do that. And what about sunlight?
Yeah.
No, not really. You know, really sunlight is just energy. It's just heat and light, of course. There's no real chemical involved in that. So, if you get up into the higher levels of chemistry and physics, they start to talk about particle effects of light. But for the most part, light doesn't have any chemicals in it. It's a chemical-free thing. Neat, huh? All right. Units of conversion, or of measurement, and of conversion when we get to it. So now, this is actually a very big point. It's a very minor point, but it actually can cause a lot of problems. When you do a measurement will contain a number and a unit.
I just have a quick question. So the learning check we just passed is
Yep.
going to be on our next quiz.
That could be on your next quiz.
So is
If,
any one of them?
if we only get through this one, then this will have to be the one that's on your quiz. But I'm pretty sure we'll get through one or two more anyway. And if that's your quiz, then that's your quiz. If we get through another one, the other one might be your quiz. So,
The exact question?
yep, cut and paste. I'm not trying to hurt you. I'm trying to help you. What's that?
Fruit and milk.
Fruit and milk. Yep.
Are we not eating right now?
No. That would be too easy. Okay? Great questions. All right, now, a measurement. You can read the slide if you like, but first of all, a measurement. A measurement must contain a number and a unit. So let's take a common measurement, your age. If I were to come in here and say, I was 424, you'll all be like, what? You're not 424 years old. No, I'm not. But maybe I'm 424 weeks old, right? Do you see how the unit mattered there? Now, if I say I'm 40 years old, okay, well, you could probably understand that. But if you look at a baby and you say that baby is 40, what? The baby can't be 40 years old. Well, it's 40 days old. The unit changed. So the number and the unit have to be together, or else the number doesn't mean much. Do you see what I'm saying? What way is it to Miami? 60. 60 what? 60 feet? 60 miles? 60 kilometers. If you ask a Canadian, how far away is Miami, they're going to say 120 kilometers, because they speak in kilometers. Americans will say 60 miles. Miami is about 60 miles away, right? See how the unit made a big difference. So the unit has to be there, or else the number doesn't mean anything. All right? Okay. In science, we like to use the metric system. And there's also this thing called the International System of Units, the SI system. We'll get into that a little bit. Personally, I don't get too bent out of shape about the SI system, but the metric system we do have to know. Okay. The metric system is used all over the world to do science. Some countries have adopted it, or most countries have adopted it to be their general unit of measurement. We still use what I call the English system. Some people call it the American system. I call it the English system because I'm from Canada, and in Canada we call it the English system, so I kind of brought it with me down here. When I say the English system or the imperial system, I mean the American system. Feet, inches, gallons, pounds. That's what I mean. Okay? But in this class, we do have to know the metric system. Now, if you look at this slide real quick, you will see the metric unit and the SI unit. Now, the SI unit, the System International, is just basically said, okay, whenever we talk about length, we're always going to talk about it in meters. So if you go to a conference in France, the SI units will be meters. If you go to a conference in Canada, the SI unit will always be meters. So everyone's always speaking in the same unit. That was the goal of the SI system. People still use whatever units they're comfortable with if you ever go to a conference, usually. Now, in metric, the base unit of length is the meter. That is the base unit of length. So the meter, everything relates around a meter. The base unit for volume is the liter. So when you're speaking about volumes, everything kind of revolves around a liter. Now in the SI system, that's a cubic meter. And I'll get into that in a minute what that means. SI, we say cubic meter. Mass is grams. Temperature, degrees, Celsius. Now look at that SI system. Kelvin, or K. We'll get into that later on too. Just keep that in mind. And time is measured in seconds. Okay, let's go to the top. Length. Excuse me. A meter. Just to give you an idea, a yard is about from your nose to the tip of your finger. Now, obviously, my arms might be shorter than some people's. Some people's arms are longer. But just to give it a ballpark, from your nose to the tips of your fingers, or from your shoulder, something like a yard. A meter is about a yard. They're not exactly the same, but they're close. So that's about a meter. You feel me? You with me? A centimeter, or let's do an inch. An inch is about there to there. Your first knuckle on your thumb to the tip, that's about an inch. Now, for some people that will be longer, for some people it will be shorter, but that's about an inch. A centimeter is about the width of the thumbnail from the cuticle to the living part of the nail, not the part that's really long. On mine, I have really short nails, so that's about a centimeter. Now, that's not exact, but it's giving me a ballpark idea how big a centimeter is. Okay? In liter, if you go to the store, you buy a Coca-Cola, you buy the 2-liter bottle, right? 2 liters, about 2 quarts. Not really, and that's not exactly, but it's about 2 quarts. So they're kind of sort of the same. They're not exactly the same, kind of sort of the same. Okay? What else we got? Grams. Holy smokes, gram, that's the hardest one for me, because even in Canada, we measured our food in pounds. A gram, a quarter weighs about 5 grams. So a fifth of a quarter is about a gram. A gram's not very much. Temperature, degrees Celsius. A nice warm day in Florida is like 100 degrees, right? A hot day in Florida is about 100 degrees. That's about 30 degrees Celsius. 31, 32 degrees Celsius. So it's a hot day in Celsius. A cold day in Celsius is negative 20. A cold day in Fahrenheit is 0. Right? Well, I should say a really cold day in Fahrenheit is 0. Freezing in Fahrenheit is 32. Freezing in Celsius is 0. Kelvin's even stranger. We'll get into Kelvin later on. And time, obviously, we all know basically what a second is. Okay, let's talk about meters. The meter. 1 meter is equal to 100 centimeters. And you have to know that. On the exam, I will not tell you that. You have to know there are 100 centimeters in 1 meter. You'll also have to know that in 1 centimeter, there are 10 milli. I should write this out. And that is abbreviated M. So the abbreviation for meter is the little m. Abbreviation for centimeters is cm. Abbreviation for millimeters is mm. You have to know those. Now there are more conversions than just meters to centimeters, centimeters to millimeters. There's one more. Sorry, 1 kilometer is 1,000 meters, and that is km. They're that bigger. Now, there are more than just those. There are decimeters and hecameters. There's other units in between these, but I personally don't require you to know them. I do require you to know these. Okay? And there's also micrometers and picometers and stuff like that. The ones that get really small, those are in your book. Please familiarize yourself with those so that you kind of have a feel for them. But these, to me, are the three most important ones to know. Okay? So make sure you memorize these so that on an exam, if I ask you, you could tell me that there are 10 millimeters in a centimeter. I think most of you probably already know that, but make sure that you do. Okay? All right, so that's meters. Now, volume. One quick thing, I'm sorry. Still a little rusty from the vacation. This is for measuring length. So if you want to measure length in metric, you're going to measure that in meters. Sorry, I should have given you that title. Still a little creaky from the holiday. Getting back in the swing of things. Now, if you want to talk about volume, we want to talk about liters. In the metric system, liters are what we use to measure volume. So now, in volume, we're going to talk about liters. 1 liter equals 1,000 milliliters. ml. So 1 liter L equals 1,000 milliliters ml. That's the abbreviation for milliliter. And those are basically the only two volumes that we use. There are microliters. Familiarize yourself with those, please. Microliters, and there's even picoliters. But those, for the most part, the liter and the milliliter are what we see commonly in society. Now, you can measure in centiliters. You can measure in deciliters if you really want to. Most people don't. It's kind of odd to see it written that way. If you ever go to a scientific conference, you're going to hear liters, milliliters. You might hear microliters, but you're not going to hear hectoliters. No one's going to say that. No one's going to talk about kiloliters either. That's just a really weird thing to say. What if we had 1 milliliter? That equals 1 centimeter cubed. So 1 milliliter is a centimeter cubed. So now instead of having a meter by a meter by a meter, now our box is a centimeter by a centimeter by a centimeter. Same idea, same concept, smaller box. So now it's 1 centimeter, 1 centimeter, 1 centimeter. So volume equals 1 centimeter cubed equals 1 milliliter. Okay? Sorry for the crowdedness on the board there. So now, we know a meter cubed is a liter. A centimeter cubed is a milliliter. Now I want to stop for a second, and I want to ask you a question. How many people here enjoy watching TV dramas about medicine?
Well,
Come on, everyone likes House, right? He's so dreamy. What was that one show, Grey's Anatomy, with McDreamy on it? All the girls would flutter and flirt with McDreamy on the TV. It was kind of funny. ER, Untold Stories of the ER. all these things. And on all these dramas, there's always some patient wheeled in to the ER, and they want you to push some medicine, 5 cc stat, right? You've all heard that 5 cc comment, or half a cc, or whole cc. You've all heard that, right? Did you ever wonder what a cc is? Cubic centimeter. So a cc is a cubic centimeter. A cubic centimeter is a milliliter. So when a doctor or someone says, give them 3 cc stat, they're saying, give 3 milliliters. Quickly. Right? Hopefully it doesn't kill them. Okay? So that's what a cc is. Cc is a centimeter cubed, is a milliliter. They're all the same. You're saying the same thing in a different way. All right? Is everyone okay with that? Now this thing, just so you know, for those of you taking lab with me, that's a graduated cylinder. Yep, it's graduated. It's all grown up now. It left school. Got a cap and gown. Thank you. At least someone laughed at that. Go ahead.
So we need to take a lab for this class?
No, it's not required. No. No. There's just offered. But if you want to take it, feel free. I think I have room in my lab class. That's a graduated cylinder. You're going to see them in lab from time to time. Every now and then you hear me mention the lab course. It doesn't mean that you have to take it. It just means that I'm trying to engage everybody. That's all. If you want to take lab, it'd be fun. I'm happy to have you. Okay, grams, mass. Mass and grams. Now, first things first. Let's talk a little bit about the difference between mass and weight. They're not the same. And you know that. Everyone knows that. Mass and weight are different. Simply put, mass is a measurement of the amount of matter. So in theory, the amount of mass you have on the Earth, say you have a 100-gram block of lead, in theory, that same 100-gram block of lead will have the same mass in outer space as it does on Earth, because it's a measurement of the amount of matter present in the block. Now, you may have to get a fancy scale or a fancy balance to weigh that matter in space, because most balances on Earth are working with gravity. Now, weight is a measurement of force. Now, weight basically is measuring the amount of force pushing down on an object by gravity. That's why when you go into a zero gravity environment, it's considered weightless, because there's no gravity pushing down on you. So there is no force pushing down on you. Okay? Mass is a measurement of the amount of matter that's present. Weight is the amount of force pushing down on that matter. See the difference? It's a subtle difference, but it's a difference. Okay? So, mass. Kilogram. 1 kilogram equals 1,000 grams. So if I have a kilogram, which is abbreviated km, or kg, sorry. I have 1,000 grams, which is abbreviated g. When you measure the mass of an infant, you will measure that mass probably in kilograms, if the infant's large enough. If the infant's really small, you might go to grams, but that's pretty dangerous. Most babies weigh what, 5 to 7 pounds? That's about 3 point some kilograms. Okay? If you're going to measure your own mass, you're going to measure it in kilograms. Everybody is, because we're all that heavy. If you're going to measure the mass of, I don't know, a rubber ducky for your kids, you might measure that mass in grams, because it's not very heavy. Okay, it's pretty small. If you're going to measure the amount of force that that's being exerted on you by gravity, you're going to use pounds. Okay? You're going to use a weight. You follow me? Everybody kind of okay with that? All righty then. And these are basically your two major units for mass. There is one more. 1 gram equals 1,000 milligrams. So 1 gram is 1,000 milligrams. Now, to use milligrams, if you wanted to take, say, the mass of a drop of water, you would probably use milligrams, because that drop of water is not going to weigh anywhere close to a gram. 1 drop, milligrams. So say you take a drop of water, put it on a balance, and it's going to say 9.6 milligrams. Now, again, let's quick, because I'm going to harp on this a little bit. Units are important. If you were to say, take a drop of water, take its mass, and the scale, the balance said 9.4, and you wrote down 9.4, I don't know what you mean. Do you mean it's 9.4 kilograms, 9.4 grams, or 9.4 milligrams? And there's even smaller units. There's like micrograms and stuff like that. Which one do you mean? The unit has to be there. Now, with that being said, write this down in your notes. On an exam, if I do not put the unit, I will lose at least 1 point. The unit is that important. So if you do all these great calculations and you get the right number, but you do not put a unit beside the number, if the question is 5, you will get 4 out of 5. If the question is worth 10, you might get 9, you might get 8 out of 10 for forgetting the unit. Do not ever forget units. They are that important. Okay? Most people don't forget them, but it's just to kind of to let you know, to make sure we're all on the same page. Okay? So that's mass. Pretty cool, huh? Temperature. Oh, I love temperature. Now, this is a time of year where everyone says, I love South Florida. Why? Because they watch the news, they read the paper, and they see their friends and neighbors in New York and above, up into Canada, are down into minus 40 Fahrenheit. Ooh. When I used to live in Michigan, they would call that a cuddle alert. Oh, it's time to cuddle with your loved ones. Nope, that's time to start a big fire because it's cold. Who here is not from any place that has snow? Who here has never seen snow? Wow. There's a lot of you. So you guys never seen snow. Okay, I refer to you all as the blessed few. You are blessed who have never seen that white, awful nastiness. Now, I'm going to tell the people who've seen snow, you're all going to agree with me. People who've lived in snow, driven in it, are going to agree with me. Guys who've never seen snow, here's what snow is like. Snow looks great on TV. It looks beautiful in photographs. It looks romantic. It's like, oh, we can sip hot chocolate by the fire. Oh, it's so romantic. Here's the reality of snow. Snow is wet, it's heavy, it's cold, it's dangerous. More traffic accidents happen in snow than any time other time because people slip and slide in it and they get killed. Shovel it, it's heavy. People have heart attacks trying to shovel snow. What else is there to say about snow? The cold air will leach through your walls and windows and you'll find drafts you never knew you had. Your power bills go way up. There's all kinds of nasty things that happen with snow, which is why yours truly from Canada lives in South Florida. I was there over the holiday though, and it was quite nice to see snow for a little while, but I didn't have to drive to work in it. So that was the big thing. All right, that being said, temperature. Temperature. In the metric system, we use either degrees Celsius or Kelvin. We use either one. Now, in the SI system, Kelvin is used primarily. Kelvin is used primarily. Now, and obviously, we all know that in Fahrenheit, we use that in general day-to-day, telling each other what the temperature's like. So if someone says, hey, what's the temperature, and you say it's 80, then we all know, if you're going out to the beach, you should put some shorts on, maybe a hat, sunglasses for sure, because it's going to be bright and sunny, right? We also know that if someone says, oh, it's 32, we all know that, it's cold, right? Now, that goes back to the unit again. If I say it's 32, and I'm speaking Canadian, they're going to put shorts on, sandals, hat, they're going to have suntan lotion, they're going to get ready to go to the beach, because 32 degrees Celsius is a blistering hot day. 32 degrees Fahrenheit, though, is a really cold day. Okay? That's where the units matter. Okay? Depends on who you're speaking to. Now, speaking to someone that you know has lived here a long time, they're probably working in Fahrenheit, so you could say 32 and get away with it. Or you could say 82 and get away with it. Other people may not like it. Now, let's look at Kelvin. Let's talk about Kelvin real quick. Kelvin, wow. That's a weird one, right? Most of you, probably all of you, have never heard of that before. Kelvin. What is this odd temperature scale you're making up today? A few other things. Celsius is based off of water. Believe it or not, it's based on water. Water will freeze at 0 degrees Celsius. So the freezing point of water was determined to be 0. The boiling point of water was determined to be 100 degrees Celsius. So between freezing and boiling, there's 100 degrees. Okay? You with me on that?
0 Celsius.
0 Celsius, water will freeze. 100 degrees Celsius, water will, okay? In Fahrenheit, it's 32 degrees, it'll freeze, and what, 212 it boils? Something like that? 212? 212? Okay. 212 it will boil. In Celsius, it's 0 and 100. Okay. So now, Celsius was pegged to that. So we use the boiling point of water is the freezing point. Sorry, the freezing point of water is 0, the boiling point is 100. In Kelvin, they don't use water. They use this other thing called absolute zero. Write that down. Absolute zero. And we're going to talk a little bit more about Kelvin too. I just wanted to introduce it today to give you a little preview of what's coming ahead. Absolute zero is a very interesting phenomenon. First of all, we've never achieved it, and we probably never will. We've gotten really close to it, but we never got to it. Absolute zero is the coldest temperature achievable in the universe, we believe. Okay? Absolute zero is the coldest temperature achievable in the universe, we think. We believe that to be true. And Kelvin is based on it. So Kelvin is based on absolute zero. So 0 Kelvin is as cold as it can get. We think. We've never actually achieved it on Earth. Gotten really close, but never got there. Hello?
What's the temperature for dry ice?
Negative 72, I think. Or negative 45, something like that.
They use Kelvin for like cryogenics, right?
Yep. Mm-hmm. That's because cryogenics are way low. They're like 1 or 2 degrees Kelvin. Okay, now, Kelvin is based on absolute zero. So 0 is as low as it can get. So you can't get negative 10. Like there's no negative 1 Kelvin. It doesn't exist. But 273 is the freezing point of water. And 373, water will boil. So that's Kelvin. That's just a little quick intro to Kelvin. We're going to get more into it later on. But for now, just write that stuff down so you have a little familiarity with what Kelvin is and with what absolute zero is. Absolute zero is the temperature, the lowest temperature we believe can be achieved in the universe. Time. Time is measured in seconds. That's just how we do it. Time is measured in seconds. Oh, sorry, go back. All right. No, now it says here, what are the SI units? Don't worry about SI units. Just what is a unit? Just name any unit we can use for volume and metric. Doesn't have to be the SI unit. So for volume, what units can we use? Liter. What else? More. What is it? CC is cubic centimeters or cubic meters, right? We could use all 4 of those, or 5, however many there were. We could use all of them for volume.
So if you have this question on the quiz, what would it read?
It wouldn't have the, well, I wouldn't use that one because it says SI.
So what would it be?
I'm not going to use it.
Okay.
I promise you right now I won't use it. I'll give you my pledge as a gentleman. Okay? But I do want you to know what units you could use for all of these. Okay? So we're going to go over it. So for volume, liters, milliliters, cubic centimeters. You could use either 4. The SI unit, by the way, is meters cubed. Mass. What could you use for mass? Grams or kilograms or milligrams. Let's say you wanted to weigh the mass of that cup right there. How would you do it? And probably in grams, right? Unless it's filled with lead, and then you'd use kilograms. Okay? How would you measure the mass of, I don't know, a piece of straw? Probably in milligrams, right? It's probably pretty, there's not a lot of mass there. All right, very good. Length. How would you measure length? What's a metric unit for length? Meters, kilometers, centimeters, millimeters, right? Everybody okay with that? Those are your basic units for measuring length. Now, what if you wanted to measure the length of this table? What unit would you use? Meters. Which one? Meters. Meters. You probably use meters. You could use centimeters. It'd be kind of weird, but you could. You could even use millimeters if you wanted to. What if you wanted to measure the length of this marker? Centimeters. Probably use centimeters, right? What if you want to measure the length of your pinky fingernail? Probably millimeters, right? That's probably what you want to use. Now, you could use any unit you want inside a metric. This number is going to get really big or really small. It's kind of weird to use the really big or the really small. Okay? Everyone's satisfied with that? Temperature in metric, what would you use? Celsius. And there's the other one we talked about? Kelvin. Kelvin is the international unit, but I would accept it as an answer for Celsius too. Very good. Scientific notation. This is fun. Now, get your paper out. We're going to do some problems together on this. Scientific notation. Now, in science, chemistry, and all sciences, we work with really big numbers. We work with really small numbers. And we need to have a way to notate them easily and cleanly. Now, take, for example, this young lady. She has a really nice hairstyle, really nice head of hair. She probably has numerous hairs on her head. If you took one of those hairs and tried to measure the diameter of that piece of hair, you're going to get a really small number, aren't you? But the number of hairs on her head is going to be a really big number, isn't it? So you need to have a way to note these things to make the numbers look nice and clean. Now, there's a whole drawn-out mathematical way of thinking about this stuff. And I can teach that to you if you like, but I'm not really concerned that you understand the mathematics that much. But I am concerned that you understand how to do it. So now, let's take a look at this number. 2,400. I want to convert 2,400, which is what's called, let me just write this down here, 2,400 meters. This is standard notation. Standard notation. So that number is in standard notation. It's just a normal way of looking at a number. I want to convert that to a scientific number. So I want to go from standard notation to scientific notation. I want to convert one to the other. You do the same steps every time you do it. You follow the same steps. Okay. Now, here's how I like to teach it. The book does a little bit different way. If you like the book's way, please feel free. It will work. My way, I think, is more fun. It's just a cute way of doing it. Every scientific number will have a number written here, over above this space. That number is called the coefficient. It's just a fancy math word, coefficient. Every scientific number will then say times 10, and there'll be another number written here. So there's a number here, the coefficient, times 10. There'll be a number here. This number is called the exponent, or the unit. Okay? So every number will have this. You always have times 10, and then a number goes here in the superscript, and a number goes here. So you'll have two different numbers. Okay? Are you with me on that? Every scientific number has that. Okay. Now, what number goes here and what number goes there? That's the question. It's easy. This number here has an imaginary decimal point right there, doesn't it? Just an imaginary one. It's not there, but it's imaginary. Okay, let's consider that little decimal point there to be a small little bunny rabbit. Okay, bunny rabbits? Everyone? Everyone okay? Okay. Now, the bunny rabbit always wants to get behind the first number. The first number, the 2. The bunny rabbit wants to be behind it. You all with me? Wants to be behind it, which behind it I mean it wants to be right here on the right of it. Call it the bunny rabbit's home. It always wants to jump home. Okay? Are we with me on that? So now, to get there, the bunny will hop. 1, 2, 3. The bunny has to hop 3 spaces to get home. Follow me? Everybody okay so far? So now, the number that we put here will be 2.400. Because the bunny just jumped to home. It just hop, 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 got home. So far, so good? Everybody? How many bunny hops did he do? 1, 2, 3. A 3 goes there. Okay? Now, if the bunny jumps from right to left, this number is positive. If the bunny jumps from right to left, the number is positive. Okay? So far? Everybody? And that's it. So the answer here would be 2.400 times 10 to the 3 meters. Right now, let's just put the 0, 0. I'll show you later on how to round that off properly. But you're right, it would have been 2.4. Okay? But I don't want to get into that just yet. Is that your question too?
Yeah.
Okay. All right, so that's how you do it. Now, what if the number was smaller? What if it was 0.0024 meters? Now we have a smaller number. So now the bunny is right here. The bunny always wants to go behind the first number. So he wants to be right there. So the bunny, if you're going to write this in scientific notation, let's just write that up, times 10 to the something. So that all scientific numbers have this in common. All of them do. So now the little bunny is going to hop 1, 2, 3 to go right there. So the number that goes here is 2.4. Now, the bunny did 1, 2, 3 little hops. But now he went from left to right. So put a negative sign here. Times 10 to the negative 3. Okay? Does that make sense? 10 to the negative 3. Now I can explain the math behind this if you'd like. I've tried a few times in class with this class, and students kind of get a little freaky on me when I do that. So I just like to bring in the bunny, the little bunny hops. Okay? If you want me to explain the math, why this works mathematically, please see me after class. No problem to explain it. It's not that challenging. It's just a little weird. Okay? So the answer here would be 2.4 times 10 to the negative 3 meters. Okay? That's all there is to it. It's not hard. It's really not hard. Everybody at least a little bit content and happy? All right, let's get some examples here. There we go. Why don't you guys try this on your own? You're welcome to work in teams. You don't have to work on your own. If you want to work with a friend or meet a new friend today, you're welcome to talk to each other. And I'll come around and take a look at your work here. I may not get to all of you, but I'll try. Let's try to do these on our own. They're not hard. So if you think it's hard, get that out of your mind. It's not. How'd everybody do?
Good.
Anybody still trying? Was it hard? No. Not too bad, right? Everybody likes to hear about a little bunny hopping around. Kind of makes you feel fun and festive, like a small child. All right, let's do them up real quick, and then we can move on. Okay, so now we have 64,000 grams. In standard notation, so to convert that to scientific, you're going to have times 10 to the something. Okay, so now, where's the little bunny hiding at? Bunny's hiding right here, right? 1, 2, 3, 4 to get behind the 6. So it'll be 6.4000. We'll leave those zeros for now. I'll show you soon how to get rid of them. Now, how many little hops did the bunny make? 1, 2, 3, 4. 4 little hops. So 6.4, that's kind of small. Sorry, let me write that a little bigger.
So you bring the measure of the unit after the end of the problem.
Yeah, at the very end, yep. Okay, so that's 64,000. 0.021 meters. Let's convert that to scientific. So it's going to be times 10 to the something. Okay. The little bunny has to hop behind the first real number. So 1, 2. So it's going to be 2.1 times 10 to the 1, 2. And that bunny came from the left to the right, so you have to call that a negative hop. Negative 2 hops. Oh, thank you, unit. See, I would have got that wrong. Punishment. Okay, good. So everyone got those? Everyone's doing good then. All right. And 138 milliliters. 138 milliliters equals, bunny's right here, 1, 2, 1.38 times 10 to the negative, not negative, positive 2 milliliters. All right? Everybody get all those right? Yes. All right. If you didn't get them all, that's okay. Try them again. One little quick piece of advice for solving problems. In class, right now with me, everything seems easy because I'm going over it with you. It's fresh in your mind. When you get home tonight after work or whatever you plan to do after class, try it again. Make sure it's still easy for you to do. If it's not, go ahead and practice it. In the assigned problems in the back of the syllabus, there are some of these you can practice with. Go do them. On Mastering Chemistry, there's some of these you can practice with. Go do them. It's really easy. This will be on your exam. It'll be worth probably 5 points. That's 5 quick, easy points if you can do this quick. If you can't do it quick, you're going to be stuck on it, and you might burn up a lot of time trying to do the easy stuff. You don't want that to happen to you. All right, here we go. Everyone okay so far? All right. Measured numbers and significant figures. Write that down as a big chapter heading, or chapter 1.5 heading. Hi.
In the notes, the other slides, you just skipped that?
Yeah, I skipped over them. You can review them if you want. It kind of is the mathematical explanation of how this works. But as I said, I've tried to explain that a few times to this class, and a lot of students, they have a hard time grasping it. And probably the reason is because I'm not a math teacher. I'm a chemistry teacher, so I have a hard time explaining math. I can explain chemistry all day long. Explaining math, it makes sense to me, but it probably won't make sense to anybody else because, I'm not a math professor. So, but I can try if you want to come and talk to me, I'm sure we'll both get frustrated to the point where we just say, yep, we get it, and walk away. But I can try. All right. Measured numbers and sig figs, or significant figures. You'll hear me refer to them as sig figs a lot. Now, write this down, please. Measured numbers are numbers obtained when you measure a quantity. So measured numbers are numbers obtained by measuring is what that basically says. But it's true. If you go to the scale, you step on the scale, you'll get a number. That number is a measurement. It's how much you weigh that morning or that day. That number is a measurement. Now let's say you get on the scale and the scale says 210. Okay, that's mine. Okay, I'm 210. Scale says 210. Now, let me ask you a question. Do you think I weigh exactly 210? Or do I weigh maybe 209? Or 211? You see what I'm saying? Now, if I get a better scale, or a better balance, I get on the scale, it might say 209.684. So that's a better number, isn't it? It tells me a lot more digits. It gives me a more accurate reading of how much I actually weigh that day. Let's say I get an even better scale, 209.684,521. It's a better measurement, isn't it? It's got more digits. It gives me a more accurate assessment of how much I weigh that day. Those are measurements. You follow me? But the first measurement, 210, and the last measurement, they're kind of the same number, aren't they? More or less. They're both right around 210. But one is not as accurate as the other. Does that make sense? Okay? So keep that in mind. So when you measure something, you can always get a better measurement. Always can. All right. Measured number. Now, please write this down. We're going to do an example here in a minute. This is not going to make any sense to you until we get to the example. So please just write it down. And then once we do the example, you'll be like, oh, that's what that meant. And it'll be more clear. To write a measured number. Now, this is how we do it in science. In science, scientists, we do it this way. Nurses do it differently. When you get to nursing school, they'll teach you a slightly different method. It's a little bit easier than this. But this is how we do it in science. To write a measured number, you observe the numerical value of the marked line. So like your bathroom scale, it has little lines with numbers written below them. That line represents that number, right? So say the little arrow points at the 210. Okay? So that's your first number, 210. You estimate the value of the number in the marks. What on earth does that mean? Don't worry about it. Write it down. We'll get to it. In the example, it'll become very clear what we're going to do. The estimated number is the final number in your measurement. So the estimated number, that number between the little marks, that's your last number. It'll make more sense in a second, I promise. To try to explain this in words is very challenging. But please write that down. And I promise it'll be very clear in a minute. Okay. Does that make any sense to anybody? It doesn't, right? Kind of, but not really. You need to see an example. All science is like that, or almost, I should say all chemistry is like that. You can say it in words, but it's so much easier and more clear when we do examples. And for the harder topics, I'll do more than one example. For the easier ones, I'll just kind of do one. Okay? Everyone got this written down? Everybody good? All right, here's our example. Let's look at the top one only. Ignore the bottom two for now. This is just the top one. So now we have a piece of wood, and we want to measure the length of that piece of wood. So now, observe the wood and observe the ruler. So here, we know the wood is between 4 and 5 centimeters, right? That, don't we? It doesn't hit the 5 though. So it's not 5, it's 4. Right? It's 4. So you can't say it's 5 because it doesn't hit the 5, so it's 4. So write down a 4. The 4 you can read directly off the ruler. Is that correct? You can read the 4. It's right there. So now the next digit you're going to write down is called an estimated digit. Why is it estimated? Because it's not written on the ruler. We're going to guess. So now, you know that this is not 4.0. 4.0 will be right there, right on the old 4, right? It's beyond that, isn't it? It's out here somewhere. That's about halfway between 4 and 5, isn't it? Approximately. Now, we don't know if it's exactly 4.5, do we? Because there's no number there to tell us. We're estimating, that's where it is. We're guessing. We're giving it our best guess. You see what I'm doing? So I'm going to say this number is 4.5 centimeters. This, the 4, I measured directly off the ruler. So far, so good? The 5 is my estimated digit. That is the estimated digit. Okay? Now, the estimated digit is always the last digit in your number. Always. Okay? So far, so good? So now, the top ruler, we can only measure 4 centimeters or 5 centimeters. There's no little lines in between. So you with me so far? So we can only say it's 4, that's our measurement, and the 0.5 was our estimate. Now, let's take the same piece of wood and buy a better ruler. So now, our ruler has little tick marks between the 3 and the 4 and the 4 and the 5, doesn't it? This is a more accurate ruler. So now, again, we can look at this ruler and we can say, okay, it's 4. We know the wood is greater than 4, but it's less than 5. So we know that that piece of wood, and this is ruler A, this is ruler B, we know that piece of wood is 4. Point something. We don't know what it is yet, but let's take a close look at the ruler. Now, look right here. There's little graduations to help us. Look. 1, 2, 3, 4, 5. And there's 6 right there. The wood doesn't quite hit the little 6 hash mark though, does it? But it certainly doesn't hit the 5 either, does it? It's a little bit beyond the 5, but not quite to the 6. Is that true? So it should be 4.5, right? Does that make sense? 4.5. These are both measured because I read them both from the ruler. Do you follow me on that? So both of these numbers I can get from my measuring device, be it a ruler or a scale or whatever it is. Okay? Are you with me? People in the back. Who said no? It's okay if you said no. We'll go over it again. Okay. I misheard you. Okay. So both of these numbers I get directly from the measuring device. Now, I must always, this is a rule. Whatever you can read off the ruler or the measuring device, you go 1 digit more. That's your estimated digit. The only exception to that is digital. If you're using a digital measuring device, you do not do this because the digital will give you the estimated digit. So for anything else, you have to do this. Okay, so now it's 4.5, and now it's between the 5 and the 6, isn't it? So it's 4.55, because it's halfway between the 5 and the 6. You with me on that? Everybody? So it's 4.5. This is the estimated digit. Okay? The estimated digit is your best guess as to where that little thing falls, where the piece of wood falls, or whatever you're measuring. Okay? So let's look at C together. C, we have a shorter piece of wood. Now, it appears that that piece of wood stops right at the 3, doesn't it? Kind of looks that way, don't it? So what do we do there? I mean, it's not 3.5 because this is right there. It's right on the 3. What do we put? 3.0. Because it appears that the wood stops right exactly on that little hash mark. So you would say it's 3.0. Are you with me on that? Everybody?
Would 3 be a correct answer?
No. And that's a great question. And here's why 3 wouldn't be correct. Because you can read the 3 off the ruler, right? You always have to have one more digit beyond what you can read from the ruler. So this ruler only allows you to read 1 digit. So you have to have 2 digits in your number. See what I'm saying? If it, say the wood had come in here somewhere, say it was right there, you would have said it was 3.3 centimeters. You feel me? We're good? Everybody else? All right. And that's how you measure. Question? Oh, okay. All right. Is everyone okay with that? Okay.
0 would be considered your estimated digit.
Exactly. Exactly. Very good. The 0 would be your estimated digit. Okay. Write this down. Big and bold. A number is significant when. And this is a great thing to go over last thing in the class. Go home and read this over and do the problems in your book and on mastering. Because this is a big deal. It seems hard when you first start it, but it's not. It's actually very simple once we start doing examples. But for now, it's going to seem, what on earth are we talking about? So just write the rules down and we'll start doing examples. Okay. A number is considered significant. Now, significant means that it was either measured or estimated. That's more or less what significant means. So, in a measurement, if a digit is not 0, it is significant. That means you must have read it off of a measuring device. Okay? You with me on that? If you're not 0, you must be significant. A 0 that is between 2 digits that are not 0 is significant because you must have read it off a measuring device. Okay? This will all make more sense as soon as we start doing examples, I promise. A 0 at the end of a decimal number is significant. Why? Because you had to measure it to get it. So 50 decimal point is. And a coefficient in a scientific number, the coefficients are always significant. All right? So write that big and clear. It's going to seem really strange for a few minutes, but let's stay with me, bear with me, we'll do our best. Everybody got it? So it's a lot. That's why it's kind of good to have the slides, but you didn't know till today. Excellent. Okay, 5 minutes left, guys. So we can do it. We can do it. Got it? Excellent. All right, here's some more rules. A number is not significant. Now, this is just as important as when they are significant. A number is not significant when it is at the beginning of a decimal number. Those are called placeholders. They're telling you the number is small. When the number is at the end, when the zeros are at our end of a number and there's no decimal point. Now, notice, this is a kind of one. Right here, there's no decimal point there. So those zeros are just holding a place. They're telling you the number is big. But they're not giving you any indication of what these digits are down here because we didn't measure them. We don't know. Because no one told us. We didn't measure them. Okay? So these are the rules for significant figures. Now, not sent yet because you haven't. We'll start doing examples here right quick. We'll get a few of them done before the time expires, and we'll pick it up here next week, and we'll do some more examples of this. It's really easy once you get the swing of it. But to get the swing of it, you kind of have to practice it. Everybody got it? It's a lot to write down, I know. It's a lot. Yes? Yep. All the stuff that I'm presenting on the slides is in the book. Why? You look perplexed? No? Yeah, all these rules are written in the book. Mm-hmm. Got it? All right, cool. Here we go. A couple of examples. Now let's do these together. Number A, or letter A, 0.006265. That's a great example. It's actually a little bit hard. 0.002650. 2650. We got meters? Okay, meters. Now I want to know what digits in that number are significant. That is to say, which ones were measured. 4. 3. 3 and 4. So we have two answers, 3 and 4. So let's talk about it. Let's go. Good answer. Good. Whoever said the other answer too, good answer. I haven't told you which one's right yet. Let's look at them carefully. Now we know that these ones are significant, right? Because they're not 0. Is that correct? So these 3 at least are significant. What about these 3 in the front, these 3 zeros? Are they significant? No. They're called leading zeros. They're leading up to the number. They're holding a place to tell you the number is small. It's below 1. Okay? They're not significant. They definitely weren't measured, but they're telling you the number that you're looking at is small, 0.003. You with me on that? Everybody? Hopefully a little bit? Okay. So those are not significant. The question is that 0 significant? Yes. Yes, it is. That is your last estimated digit. Oh, that is your only estimated digit. Okay? Now, here's a little rule that the book doesn't make very clear. It's not really a rule, it's kind of how I look at things. If you have a number that looks like this, and it's a small number, it has a 0.0 something. So here we go. If you have a 0 right here, so the number here is 0. It's not 10, it's 0. All the zeros leading up to the first real number are not significant. So the zeros are not significant. As soon as you hit a real number, so you're after a decimal place, and you're after the first real number, all the zeros after the first number are significant. Okay? So after the decimal place and after the first real digit, the first non-zero digit, everything beyond it is significant. So if there had been 3 zeros here, all 3 of them would have been significant. Okay? Because you're after the decimal place and after the first digit. You with me on that? Okay? So the number here is 4 significant figures. These 3 plus the 0. They're all, those 4 are significant. The leading zeros, the 0.00, those are not. That was a tough one. It's a tough one for the first question. But for those of you who got it right, good. For those of you who got it wrong by just the 1, good. You're still doing okay. 43.026 grams. How many significant figures are in that number? 5. Who thinks it's 5? Who thinks it's less than 5? Who thinks it's more than 5? Can't be more than 5, right? Okay, that 0 is called a sandwich 0. It's between 2 real digits, 2 non-zero digits, so it is significant. Okay, so it had to have been measured. Are you with me, everybody? And the last one's pretty challenging too. 1044000. So this 0 here, I think everyone here will agree is significant. It's between 2 non-zero digits, so it must be a significant number. The question is, are these 3 zeros significant? Who thinks they are? Who thinks they're not? The nots have it. It's a democracy today. They're not significant, and here's why. There's no decimal point here. Now, let's talk a little bit over here. Let's talk a little bit over here. If I write down the number 10, that number has 1 significant figure. Are you feeling me? So that's 1 significant figure. If I write down the number 10 decimal point, that's 2 significant figures. The decimal point tells me that I measured that 0. That 0 is my estimated digit. Okay? This tells me that that 0 is a placeholder. Okay? That's like saying, well, we all have that friend, right? You go to the movies, that friend is always $1 short. So you ask that friend, hey, you got $10 for the movies? Oh yeah, I got $10. You know he doesn't, right? You know he's got 9, right? But then if he goes, oh yeah, I got $10, no problem. Yeah, I do have $10. He digs out and shows you, that's 10 decimal point. If he goes, oh yeah, I got $10, that's 10, no decimal point. You don't have a lot of confidence in that number. This one you have more confidence in, right? Now what if that same buddy says, I have $10 and 1 cent? That's 4 significant figures, right? How much confidence do you have in that number compared to that number? A lot more, right? Because he's giving you more information. He says, I got $10 and 1 penny. He knows down to the penny how much money he has. That's 4 sig figs. Okay? And I jumped over 1. 10, 0 is 3. Okay? So that's what significant figures do for you. They give you more confidence in a number. All right, now that the class is up, you're free to go. One quick announcement.